Okay, now we're going to see how to use Pandas to visualize data, either using pyplot on the data that we have in our tables, or actually using some wrapper functions that Pandas has that makes it easy to do some more sophisticated plots with pyplot indirectly, because we'll be accessing the visualization functions through Pandas. So let's once again, this is not to give you a very exhaustive and detailed look at different techniques. This is just to give you a few examples. And this week marks a substantial change in the way this course progresses, because now I'm going to start focusing on things that are a bit more sophisticated, may be useful for you in the future. They may be useful for you right now on the work you're trying to do, but maybe you don't need to learn them now for your final assignment or for whatever you want to apply Python to. So we are going to start focusing more on what you want to do, each of you wants to do with the final assignment. And these lectures will be more to expand the horizons and give you a notion of things that can be done. So I'm going to start with giving an example of kernel density estimation. So this is one way of representing distributions of values, and then plotting directly from series and data frames by grouping the values and doing some other more sophisticated plots, like box plots, for example. So let's go back to this star catalog data. We have the CSV file with the different stars and the distance to our solar system here, the absolute magnitude, the spectral type, and so on. And let's say that we read this file. We saw how to do this. I'm going to use load the pyplot library and use the Seaborn style for these plots. So this makes them look better. It's optional. You don't need to use. There are other styles if you want to experiment. I personally like this one. And now I read the catalog using the read CSV function from Pandas. So this is a data frame with my data as a table. And now we saw this in the last lecture. I can get the count of all the different values in the spect column. This is the spectral type column here. And if I take the first 5, this gives me the 5 most common spectral types. So now I could do a histogram of the magnitude for the most common type, for example, K0. I can select this most common type. So this is the first entry in these counts. I can get from my data, from my table, the column corresponding to the absolute magnitude. And here I want the rows that that correspond to those rows where the spectral type is this most common type. So this most common type is the K0 here. I'm comparing all the spectral types with K0. So this is a series of true and false. And I want from this column only those entries that correspond to a true in this condition. So this will give me a series that has only the absolute magnitudes of the stars of the K0 spectral type. So now I can, from this series, ask for the histogram with this number of beans, and then I can save the image to a file if I want, because this histogram is actually calling the functions in pyplot. So you can use the savefig function in pyplot because it has the plot in memory, and you can save it to a file. So this would be the result of the histogram. And as you can see, we did a fairly complex manipulation here. which is getting the most common spectral types, finding the one that is most common of all, getting the absolute magnitude of the stars of that spectral type, and then plotting a histogram. And this is just 4 lines of code. So you don't need to implement many things if you know how to use Pandas. This is very easy for extracting the plots that you want, creating the plots that you want. But let's do something a bit better. I personally don't like histograms because they bin the data into discrete segments, and then you have these discontinuities, this stair-like look, depending on where the points lie. And if you change the bins a bit, you can the look of the histogram can change quite a lot, because some points now no longer fall in one of the bins, they fall in the one on the side, and the whole plot looks different. So I prefer to use kernel density estimation, which is a smoother version of the histogram that we can compute by, instead of placing each value in a bin and counting 1, we can consider a kernel function, which is just a function basically that has an area of 1. It's symmetrical around the 0 coordinate, or in this case it's going to be centered on each point, and it's positive. So it can be something like a triangle, a Gaussian curve, cosine, something like that. So for example, let's use Gaussian curves. This is a common one. And we're going to add the curve for each point. So these are the points that we have here. Instead of plotting a histogram by drawing the boxes, counting the number of points in a box, we add these smooth Gaussian curves centered at each point. So here, where we have one point that is alone, this is just its own Gaussian curve practically. Here it's the sum of these two, but now we have 3 points here, so this rises up and we have a larger peak here. And this is like a histogram, but it's smoother, and we can control it better by controlling the width of this Gaussian curve. So it's easier to visualize the data with kernel density estimation. So instead of a histogram like this, we want to draw a kernel density estimation graph like this one. Okay, so let's do this for the 5 top spectral types, because it's only a line for each one. We can easily superimpose them. And we're going to create a function that computes the x and y values for the plot. So these are the x values here, the y values form this line, and what we need to do is to compute the kernel density estimation for a large number of values on this axis, so that we get a smooth curve, because if we compute only for a few values, then we get jagged edges on the plot. So we're going to use SciPy stats. This SciPy is a library for scientific computation, has this statistics module, and we're going to import the Gaussian kernel density estimation object from there. And this is easy because we just give our data points to the Gaussian kernel density estimation, and this returns a function that we can use to input some x value and obtain the y values for the kernel density estimation. So this may be a bit confusing at first, but this function, Gaussian KDE, returns an executable object. So it returns a function that is created for mapping any input on the x value to the y value corresponding to the sum of these Gaussian curves. So we can ask for any x value, what is the sum of the different Gaussian curves, and it will give you the total value there. So what we're going to do is create a series of points. This is the number of steps that we want, for example, 200, 500, something like that. This is the number of points that we're going to distribute evenly on the x-axis. And we're going to do that using this linspace function from NumPy. So we have the minimum value, it's the smallest value in our data set. The maximum value is the largest that we have here. And then we're going to spread out evenly points between these two extremes, this number of points. And this gives us this x-axis here. Now we need to compute the corresponding y values for the kernel density estimation. So we use the Gaussian kernel density estimation with the data to give us the function that can map from x to y. And now we obtain the y values by giving it these x values for the x-axis. So all the uniformly distributed values here on the x-axis, and we get all these y values computed. And now we can just return the two, the x and the y, so we can do the plot. So this is just a simple auxiliary function to help us plot. And now we're going to use the top 5 most common spectral types that we got from here, from our table. We're going to iterate through these, the top 5. We're going to obtain the values of the absolute magnitude for all stars that have that particular spectral type. So we're going to run through the top 5. Oh, sorry, this is just an optional print here, so we can see the mean of the absolute magnitude, but this is not necessary. This is just if you want to follow the execution of your code. But now we're going to plot these values, so the values of this series. And if you take a Pandas series and you use the values attribute, this returns a NumPy array with just the values in that series. So it ignores the index and just gives you the values, which is what we need for this particular case. And now we get the x and y values for the plot using 100 points on the x-axis. And now we plot this, and we can now create a legend using the different spectral types. So remember that this one has the top 5 spectral types. If we use this as the legend, it will put the 5 strings as labels for the different series that we plotted. And since we are plotting in the same order, then we get the correct labels in our series. Now we can save the plot, and we have this result. So these are the top 5 spectral classes in order, so the ones that are more common. And this is the distribution of the absolute magnitude of the stars in each of these spectral types. We can see the kernel density estimation giving us those distributions. Okay, so we saw here, in this case, we did the plot outside the data series, but the series have plotting functions. For example, let's go back to the table with the government expenses that we saw previously. We get the price series, and now we can, for example, compute the total cost by using the cumulative sum of the prices. So prices is a Pandas series that has all those indexes and the price, because this is the column that we are looking at. Now we can create a new series that has the same index but has the cumulative sum of all the values. So it's going to add all the values and give us this sum, and we can now ask to plot that series. So we just call plot on the series, and the Pandas series objects wrap the plotting functions from pyplot. So if we ask the series to plot, we get a plot of the series. This is the cumulative sum of the prices as we go along the index on our table. So we can do things like this. We can, for example, expensive contracts are those for which the price is larger than 50,000 euros. So we get the expensive contracts by, from the table, selecting these rows here. And we can now, from the expensive contracts, select the price column and ask for a histogram. So this is the histogram of the expensive contracts that go all the way, I think, to 2 million euros or something like that. And now we can do the same thing for the cheap contracts, which are up to 5,000 euros. We create a new mask for these. We select the rows. So actually you could do this like this, omitting this line. You don't need this line, but the difference is that if you do something like this, if you have very long expressions, the code starts to get confusing. With this solution, you can actually use the name of the mask. So cheap mask gives us an idea of what we are trying to capture with this condition. And now it's easier to understand. Sorry, here should be the cheap mask. So this is easier to understand what we are doing in this instruction. So here we are selecting the cheap contracts with the cheap mask, and this is the histogram for those. So basically, with Pandas, you can easily select the data that you want, and then you can use the plotting functions from the series or even the data frame to do the plotting for you. So let's try to do some bar plots with the mean price per contract type. You have a group by function in the data frames. So remember, this table is our data frame with all the contract information for the files that we loaded. And group by allows us to specify which columns we are going to use for the group. So in this case, we're going to use the contract type, tipos de contrato, to group our rows. We're going to select from those groups just the price and compute the mean as the aggregate. So basically, this groups all the contracts by type and gives us the average price of these groups. And this is a new table that we get that has as index the first column, this contract types that we have here. So these are the different contract types, and the values are the means of the prices that we had. So we can easily aggregate data by grouping according to some columns and computing the kind of aggregates that we want. And now we can convert. So this is actually a group by object that we can convert into a data frame by using the toFrame method. So this is a group by object in Pandas is slightly different from a data frame, but it's easy to convert. And now we have this column with the type of contract and the price here. So basically, if we reset the index now, we have this type of contract in a column, because originally it would be the index. And this is one example of how we can do this. We have the group by object, we can convert it to a data frame and then reset the index, and we can check the different columns. One is the type of contract, which is what we use to group the object, and the other is the average price for each group. Okay, so now that we extracted this aggregate, we can plot like this. So to put the code together, we, from our table with all the data, we group by the contract type and we aggregate the price by computing the mean. So this gives us a group by object that aggregates this column using this as the type for the groups and computing the mean. Now we can convert this to a data frame and reset the index. So we have the two columns, which is the price with the mean price and the contract type with the type of each group. And now we can just do a bar plot, for example, price plot bar, using these two columns. So this gives us the bar plot where the first column is the labels, and the second column gives us the height of all the bars. This is not a very good plot because of the large size of these labels, but we can do it a bit better. We can do a horizontal bar plot, and now we have the contract types here, and this is the average price for all the contracts. So you see something that is fairly sophisticated, which is grouping our data by one of the columns, computing the mean of another column, and then creating a plot with those results is basically 3 lines of code. So we just need these 3 lines of code. The rest is to save to a file, and you can easily compute these aggregates and visualize the results. So this is very good, Pandas, for understanding data. And I'm going to return to this diabetes data and just show you one example of visualization using box plots. So a box plot is something like this, which allows you to compare at a glance different distributions of values by looking at these representations. So basically, the box represents the 2 intermediate quantiles from 25% to 75%. So this box here gives us the idea of where half of the points in the center of the distribution lie along this range. Then we have a line representing the median. So this is the line that separates half of the points up and half down, and this gives us an idea of the asymmetries in the distribution and how wide the distribution is. Then we have these whiskers for the maximum and the minimum except the outliers. So these whiskers are indicate the position of those points that are within the regular distribution that we have here, and are not outliers. And outliers are considered to be outside a distance from the top quartile or bottom quartile that is 1.5 times larger than the distance between the 2 quartiles. So if we count from here downwards 1.5 times this distance, that would be outliers, and the same things upward. So this is the uppermost point that is not an outlier. These circles here are outliers because they are more than 1.5 times this distance greater than the top quartile here. So they go over that limit. And this allows us to see the symmetry in the distribution, the number of outliers, and all those aspects of the distribution just at a glance. So box plots are quite useful for data understanding, for looking at a glance at the distributions, and they are easy to do because we can call the box function from plot in our data, and basically we can just tell what the size of the figure is and so on, and Pandas will do it automatically. So if we do this with our data from the PMOTAN, so this diabetes data, we get something like this. And the reason for this is that our different columns are in very different scales. For example, diabetes is just 0 or 1 depending on whether or not the person has diabetes. Age can go from 0 to say 60, 70, something like that. This blood plasma glucose concentration can go up to 200. Then we have number of pregnancies is very low, and so on. So I don't recall exactly what this one is, but all of these have different scales, like milligrams per liter or years or something like that. So it doesn't make sense to represent data like this. We cannot really say that, compare, for example, the molar concentration of glucose in plasma with the age in years. That would not make sense. So quite often it happens that if you have attributes in different scales representing different things, you need to rescale everything to something that makes more sense and allows for better representation and better visualization. So one thing you can do is normalize the data. So let's put everything in a range from 0 to 1. Basically, we're going to subtract from each value the minimum of all the values in that series, and then divide that by the difference between the maximum and the minimum. So this is a linear rescaling, and we can think of this as just changing our units. So suppose you are converting Celsius to Fahrenheit, you do something like this. It's a linear operation for changing from one unit to the next. We're just doing this arbitrarily so that all our data series have values between 0 and 1. And this is very easy to do with data frames because data frames include all the functionalities that you expect from NumPy arrays. So you can create a new table with normalized data by, from the original data, subtract the minimum values, and this mean will compute the minimum for each column, and now do broadcasting on the original table. So it's going to subtract this from every row. In every row, you're going to do this computation. And now you can divide by the difference between the maximum and the minimum. So this works exactly as if you were doing broadcasting with NumPy, but you can do it with Pandas tables. And now we can create the box plot and save the figure. So typically, if you're automating data processing, you don't really want to see the image when you run the code. You want to save it to some file where then you can import it into a document or do whatever you need with that image. So this would be an example of doing the box plot with this data, normalizing the values. So note here that diabetes is just 0 or 1, so they are spread all along this block here. Then we have age, we have plasma glucose concentration, and so on. So you can see at a glance the distributions. For example, this one is very concentrated in these lower values, but then has a long tail with lots of outliers going this way. This age does not have that many outliers. Plasma glucose concentration does not have outliers, so it seems to be very symmetrical and a very well-behaved distribution. Another alternative, because converting everything into zeros and ones may not be good for distributions like this that have many outliers, because now most of the distribution gets compressed into one extreme of the interval just because we have an outlier far away. So another way of doing rescaling is standardization. With standardization, we are rescaling each data series into a series of values that has a mean of 0 and a standard deviation of 1. So to do that rescaling, we subtract the mean of the values and we divide by the standard deviation. So just to see, this is easy to do exactly the same way. We can subtract the mean of our data and divide by the standard deviation. Note that data frame objects have functions to compute the mean and standard deviation, so it's easy to just do this with the whole data, and we don't need to do this row by row, column by column, because when we do this to the whole data, this is computed for all the columns and then applied to all the rows using those broadcasting rules that we saw for NumPy. So if we do this, we have this kind of distribution. You can see here the difference. Normalization, you convert everything into a scale from 0 to 1, but this leads to a greater compression here of this distribution here because of the outliers, and the median goes down in this case. Here we are standardizing, so we are putting everything with a mean or with an average of 0. Note that the median may not correspond to the mean because of asymmetries in the distribution, but now we are a bit more we can see a bit better this distribution of outliers because we see this long tail here, even though the majority of the points is more or less distributed in the same range because we adjusted the standard deviation, and we can compare the asymmetries in the different distributions. Okay, so this is one example. You have lots of plotting functions available in Pandas. I'm not going to bore you with too many examples, but this is to give you an idea that it's very easy to do this kind of more sophisticated analysis and plotting if you know a bit of Pandas, because then it only takes 3 or 4 lines of code and you can do something quite complex. So these two alternatives, these will often appear if you're dealing with numerical data with different attributes. You will need to do some rescaling. So basically normalization is good when your data falls into some natural fixed range, for example, pixel brightness in images or things like that. But it's not very good if you have outliers, because then you'll squeeze most of the distribution on one edge of the range here. Standardization is good when you have outliers, and especially if you have distributions that are approximately normally distributed, because then you'll get something a lot neater and cleaner. But remember that rescaling is important when you are comparing data with different units that you cannot compare. So kilometers with kilograms and years and Celsius degrees or something like that. Then you really need to rescale. Otherwise, it won't make much sense, the comparisons. Another kind of plot that is easy to do is the scatter plot matrix, that allows you to find correlations between different columns in your tables. So what you do is basically you can import from the plotting module in Pandas. You have this scatter matrix function, and you can just give your data to the scatter matrix function, and it will show you the scatter plots of combinations of features. For example, number of times pregnant with plasma glucose concentration, or age, or things like that. And you can see that some seem to be correlated, others don't have much correlation. Note that diabetes is only 0 or 1, so you get a bit of a strange effect in this case. And in the diagonal, which would be a comparison with each feature with itself, you can have either a histogram or a kernel density estimation, depending on what you choose here for the diagonal. So if it's hist, you can have a histogram. If it's KDE, then you have a kernel density estimation. Or you can just leave it out. If you don't put anything there, by default it will assume that you want a histogram. So this is something that would be a bit laborious to do if you were to do it manually, because you would have to loop everything, do a matrix of plots and so on. But it's very useful to look for correlations between the features in your data. And it's easy to do with the scatter matrix in Pandas. You just get the whole result in one go. So to sum up, I just gave you a few examples. You have very convenient wrapper functions in Pandas for plotting. If you need to do something that Pandas doesn't have, for example, like we did with the kernel density estimation for the stars, we can just extract the data and use pyplot. But Pandas has lots of different functions for this, and it's very easy to do plots by grouping different categories depending on the columns that you have and so on. We're going to see a bit more of SciPy next week. We're going to do model fitting and that kind of operation. So SciPy is a powerful library for that kind of numerical computation. But I wanted to start with Pandas on this week, because it's very good not only for visualizing data if you want to do some quick inspection of your data, but also for automating things like generating reports, processing data, cleaning data, like identifying missing values and so on. Pandas is very useful for this. So if you have these kinds of problems dealing with spreadsheets and data tables, then probably you would like to take a look at Pandas and get familiarized with this library. So one example of this is if you're using data from sources like this, like OECD, Eurostat, FRED. So some of these I don't even know very well what they are. Some are for trading stock exchange or statistics given by Eurostat and so forth. But some people work with these kinds of data. And you have here a library that encapsulates the interfaces to get the data from these servers into data frames. So the kind of things that we did in the beginning with simple examples like looking up Wikipedia pages and so on, you have fairly sophisticated tools associated with Pandas that allow you to get this data live from these sources like stock exchange data and things like that. So if you are working with this kind of data, check this Pandas data reader to see if it has this interface for the data that you want, and then you can get everything in real time into data frames for processing. For this week, you have the mandatory exercise at the end of chapter 8, but mostly I would advise you to take this week and the next weeks to start planning the final assignment and to get more familiarized and a more solid knowledge and practice with the basics of Pythons, because from now on the things I'll be talking about will probably not be used by anyone, or just and they'll just be to give you ideas of things that may be useful in the lectures, and we're going to shift the focus more to start working on the final assignment and to polish up your knowledge of Python and practice the basics. So next week I'm going to talk about SciPy for fitting models to data and doing optimization, things like that. And then the last week I'm going to talk a bit about machine learning. This will be, I'm going to cover these topics very superficially, but to give you an idea of where of what direction you can take this knowledge and this course in the future. And in the meantime, in these weeks, we will start working on the final assignment, so on the tutorials, and also if you want, starting perhaps from next week when you start having an idea of the assignment, I can even schedule some additional sessions with some of you if you want help with some specific problems. But the goal is that when we finish the 6th week of the course, so the last week of the course, you have already a head start on your final assignment and you solved the more important problems and obstacles in working with Python. So for these libraries, NumPy, Pyplot, Pandas, you can follow the lecture examples, but you should also take a look at the documentation. These libraries are very well documented. You have lots of examples there, and you can find different applications and so on. So if you are interested in dealing with numerical data, look at NumPy and different ways of processing the data. Pyplot is also important, so look at Matplotlib and Pyplot if you're going to do plots. And if you are going to use tables of data, then I recommend that you take a look at Pandas and also the tutorials for visualizing data with Pandas, because there you can find lots of useful examples. Okay, so this is the lecture for today. These lectures are going to be a bit lighter in details, not like the ones in the first week, and we have a bit more time for discussion. So I'll just set things up for Zoom, and we'll meet there in the Zoom meeting. Okay, see you soon.